Okay, let's take a look at the uh, next problem here. This is asking us to solve for the Thevenin and Norton circuit, where all of the resistor values are given in the problem statement, and our source value is also given there. So they don't explicitly say, but uh, A and B over here are our open terminals. Okay, so we're having to find R Thevenin, V Thevenin, uh, and the Norton circuit, because for these two, that's all the components that we're going to need to make those up. Um, so looking here, we see that we know that the current is going to leave this battery, travel this way, come here, hit this node. It'll send some this way, it'll send some that way, hit this node, send some this way, send some that way. It won't go down this branch because it's an open terminal. Send some down this way, won't go down this branch, that's an open terminal. Okay, then they'll recombine here, they'll recombine here, and they'll form our current once again. Okay, so now let's go ahead and just start to redo our entire process for solving for these. So, step one, do we see any dependent sources? No, so we are good to go. Step two, we are not doing that today. Step two, we're going to zero out our sources. And like we said before, take this battery, turn it into a wire, and any current sources will turn into clipped out parts. Okay. So then what we'll need to do is come here and we'll uh, draw our circuit again with the zeroed out sources. So let's just do this. Bam, bam, bam. All right. Let's be R1, R2, R3, R4, R5, and R6. And then this is plus minus VOC over here. And now step three, find R Thevenin. So like we said before, we're going to work that away to VOC. And then I'm just going to do something very similar to what I did last problem, where I'll see these two are going to be in parallel. Then these two will be in series. So this will be parallel one, this will be series one. And then these two will be in parallel. That'll be parallel two. Then these two will be in series. That'll be series two. And then these will be in parallel. That'll be parallel three. So it's just combining them down. And I'll go ahead and just write these out for you down here. So this will be R parallel one will be equal to R1 is 1 times R2, which was 50 over it's R1 times R2, 1 plus 50 So we would do 50 divided by 51. And this is going to be 0.98. Okay, then our series 1 will be our parallel 1 plus R3, 0.98 plus R3 is going to be 6, so 6.98. Then R parallel 2 will be 6.98 times, it's going to be in parallel with R4, which will be 20, by 6.98 times 20, plus 20, which will give us 5.17. And R series 2 will give us 5.17 plus R5, which is 10, so 15.17. Then R parallel 3, which is going to be 15.17 times R6, which is 35, over 15.17 plus 35. And what will that give us? And looks like this will give us 10.89. And this will be in kilo ohms, and this will be the R Thevenin because it's the last combinable resistor that we had. Okay, so that's R Thevenin. Okay, so the fun part becomes determining V Thevenin. Okay, because now what we have to do is we can figure out certain values for certain nodes if we want to do that. Okay, so the way that looks like is if we were to, let's go ahead and write our steps back out. So if we did go back to OG circuits, so if we jump back up to this one, we see that here that the terminals A and B are in parallel with that branch there. Those 2 points are the same there and there. So if I can find the drop across R6, this will be V6, that will be the same drop across VAB. So VAB. So VAB is equal to V6. All right. So now, all right, 5, do find VThef. Okay. So we've got a couple ways of doing this. You can either, an option you have is to combine all of the resistors down this way, find one equivalent resistance, and then determine the current, and then work your way back by splitting up the current a bunch of times. That'll take up about a page of work if you want to do that. Another thing you could do is you could see that if we were to take our circuit and we were to say that, well, if I took these two, combine these in series, and then took that combination and combined that in parallel, it would give me something that looks like this. So this will be R parallel 1. This would be R5. Oh, sorry, R3. Yep, that'll be R3. This will be R2. This will be R1. All right. And then what we can say is that, well, this looks pretty similar to a common nodal analysis problem, because if I can find the point right here, V, and I can find the drop across this branch, then you can do a voltage division across that branch to determine the voltage across VR parallel 1. And because you know the voltage across VR parallel 1, you can do the voltage across this branch. So let's go ahead and do that. So if we go do the nodal analysis, so we'll write nodal, and we're trying to find the value V. So we'll go ahead and do this, 1, 2, 3, and we'll just call these I3, I2, and I1. So I1 plus I2 plus I3 is equal to 0, where I1 is going to be V minus, we actually know the voltage right here, it's going to be V of S. So V of S over R1 plus I2 is going to be V minus 0 over R2 plus V minus 0 over R3 plus R parallel 1, because it's the total resistance of that branch. Okay, but see, this R3 R parallel 1, we got to go find that, because now instead of working from left to right, we're working from right to left. So that way. And I'll save you the trouble. I'll write them out here. So it would be R series 1, that would be equal to R5 plus R6, which would give us 45 kilo ohms. Then R parallel 1 would be 45 kilo ohms times R4, which is 20 kilo ohms, over 45 plus 20. It's 45 times 20 plus 25 plus 20, 100 divided by 65. That should give you 13.84 kilo ohms for R parallel 1. So now we know what that value is. So if we do V minus 50 over 1 kilo ohm plus V over 50 kilo ohm plus V over R3, we said is 6. So 6 plus 13.84 kilo ohm is equal to 0. And what's going to be easier for us is if we go ahead and do this. So 1 over 1 plus 1 over 50 plus 1 over, it's going to be 19.384. Sorry, it's just 19.4 V, and then we're going to move that 50 over. So it'll be 50 over 1 kilo ohm. So then therefore V is going to be equal to 50 over 1 kilo ohm times this mess. Sorry, divided by this mess. So 1 over mess. Okay, and therefore that value of V is going to come out to be 19.4 inverse plus 50 inverse plus 1. This will come out to be 46.71 volts. Okay, so that's the voltage value here. Okay, so now that we found that voltage value, let's go ahead and do a branch division. So if we do a voltage division, and I will help you out by drawing this. So this is V. This would be R parallel 1. This would be R3. So if I want to find V of R parallel 1, that would be our parallel 1 value over our equivalent times the voltage source, which would give us 13.84 over 19.84 times 46.71 volts, which would give us 32.58 volts. Hang in there, folks. We're getting there. So now we know the voltage drop across that branch. So we know this voltage value now. So then now let's go and do one more. So if we do one more, so we do a voltage division where this is A, that's B, this would be R6, this will be R5, it's voltage there. So where this voltage is going to be equal to the 32.58 volts. So V of R6 is going to be equal to R6 over R5 plus R6 times V, which will be whatever 6 was. 6 was 35, R is 10, or 5 is 10. So 35 over 35 plus 10 times 32.58 volts. Therefore, this voltage of R6 is going to be equal to 25.34. So 25.34 volts. And because it's in parallel with those two open terminals, this is equal to our VThev. All right, and we're almost done. Last thing we got to do is solve for I Norton. But luckily, I Norton is just going to be equal to VThev over RThev, which in our case will just be 25.34 volts over 10.59 kilo ohms. Therefore, I Norton will be equal to 2.39 milliamps. All right, so this is a complex problem, but complex problems can be good for learning opportunities.